Next up, we need to work on our asymptotes for the graph. In order to do the horizontal asymptote, we need to examine the three cases of horizontal asymptotes. The first case is when the degree of the numerator, so the highest power, is greater than the degree of the denominator. This means that there is absolutely no asymptote horizontally. When the degree of the numerator is smaller than the degree of the denominator, so let's say this was 3 and that was 2, then that means that the horizontal asymptote will be 0. When the degrees are the same, as if this x squared was an x squared, that means that the horizontal asymptote will be the leading coefficient. So if there was a 2 here and that was squared, then our horizontal asymptote would just be 2. In this case, we have that the degree of the numerator is greater. That means that we have no horizontal asymptote. Next up is the vertical asymptote, which is actually the simplest one, pretty much, to find out. And you just look at the denominator and find if there is an x there. And we have x minus 2, which means that the vertical asymptote is just 2. One of the more complicated ones here is the slant asymptote. And the slant asymptote can only exist when the numerator of the top is greater than the numerator of the bottom. And this is why that horizontal asymptotes and slant asymptotes can exist. And the difference between the degrees have to be 1. It can't be 3 or 4, it has to be a difference of 1. So now to find the slant asymptote, you're basically just doing the division that's shown in your function here. So we do long division as we did before, except it's a little bit more complicated than just doing it all with numbers. We put the top under the division symbol and put our bottom outside. And initially, in order to find your slant asymptote, you try and find what multiplies with x to make x squared. So that in this case, we just put an x at the top. And now we can minus by x squared, and we get a 0 in the bottom here. But since we have an x at the top, we also need to multiply our second part here by x, and that's why we have a minus 2x here. Watch out for these double negatives. This makes a plus, and now we have 7x, and the 6 just moves down and does 7x plus 6. Now in order to turn x into 7x, we multiply by 7, so you add a 7. Don't multiply them, you have to add them together. And you do the same thing with the 2 again, and we have another double negative, so you have to watch out for that. And you get 20 at the end. And you can't multiply by anything by x in order to get 0x, because that would just be adding a 0, and that changes absolutely nothing to our top function here. Now what this means, this extra 20, means absolutely nothing for a slant asymptote. You just cover that up, because it's just 20 over x minus 2. This is not the slant asymptote. The slant asymptote is just the part you were able to divide out, which is our x plus 7. One of the most crucial parts of a slant asymptote is whether or not it crosses with our actual function. Even though it's an asymptote and the graph will be approaching the line, it can still cross over it at certain points. So in order to find out whether or not it crosses, we just make them equal to each other here. So I moved the bottom over here, so we get x plus 7, x minus 2, and I made it less simple and just multiplied it all together so that these two sides were equal to each other. And we just cross out where they are the same numbers, so we have x squared and x squared cross out. 7x minus 2x makes a 5x, so those cross out. We're left with negative 14 and positive 6. Negative 14 and positive 6 are not equal to each other, and they will never be equal to each other, so this just means that our slant asymptote does not cross with our function. Next up on our curve sketching is finding the first derivative. In this case, we have to use the quotient law we talked about earlier, which is gf prime minus fg prime over g squared. First up, we assign our sections here, so we have f is x squared plus 5x plus 6, f prime is 2x plus 5, g is x minus 2, and g prime is just 1. Once we plug this into the formula, we get this long bit on the top. We have x minus 2 times 2x plus 5, and that's minus x squared plus 5x plus 6 times 1. We don't actually need this plus 1 here, because it's just going to equal the exact same thing. And then in the denominator, we just have g squared, which is x minus 2 squared. Make sure not to put the squared on the inside, because that'll cause you troubles later, and because it's just totally incorrect. Now we can expand the top in order to cancel things out here. So we have 2x squared crosses out with this x squared, just the 2 comes out, so we still have an x squared. And the 5x minus 5x crosses out, and we're left with the minus 4x minus 16, these two combine here, over x minus 2 squared. And this is where we lead finally into our critical values that we just learned. Critical values, once again, is when we have the derivative is equal to 0 and when the derivative doesn't exist. When the derivative of e is equal to 0, we need to use the quadratic formula to find our 2 points. So you plug it into the formula, and we get 4 plus or minus the square root of all those innards over 2 times 1. And you'll have to type this into your calculator because you won't be able to do this kind of thing in your head. So we have these two rounded to 3 decimal places. We always round to 3. And then when the function doesn't exist, we just take the denominator and make it equal to 0. You find the square root on each side here, and you find that x minus 2 equals 0 and x equals 2. Values we just found, we can do our sign analysis. And I did give you the decimals for critical values, but you can also just leave it in the form that you used when you had the quadratic equation, which is 2 plus or minus 2 times the square root of 5. And it matters that it's plus or minus because it just means that there's 2 different values. Now we put it on our sign analysis and we have it going from negative to infinity because we have no restrictions on our entire graph. And we put the points that we had on our critical values, including the 2 in the middle here. And now you find a number that's smaller than 2 minus 2 squared root of 5, and you plug it into our first derivative, and it ends up being a positive number. And you do that with every single step until we get positive, negative, negative, positive. We see that it's going up here because it's increasing. So we have the maximum because it goes down right after. So we have f prime of x is greater than 0 because it's positive, and it goes into negative when it's smaller than 0. And at our min, it starts smaller than 0 and turns into greater than 0. We want to explain this when you're writing it so that anyone who's correcting, including me, can understand what's happening. So we have that f of x is increasing in the coordinates negative infinity, round bracket because it's not including, until 2 minus 2 squared root of x, and then it's a closed bracket because it does include, in union with 2 plus 2 squared root of 5, and infinity. Once again, it's a round bracket around the infinity because you can't contain infinity. And we also want to do that with decreasing, and it's just in between these 2 points here. So it's closed brackets on both ends, and it's the point and the other point. Now we have our maximum and our minimum, and you want to express that here too, but I just found that it was important to find the actual point. So I put our critical value into f, and we find the y value for that critical value for both of them. And I left those in decimals because there was no real fraction version for it. Now next up is something we've talked about, but we haven't actually done in class, and this is called the second derivative. And the second derivative is exactly what it sounds like. You're just doing the derivative of your derivative. In this case, our derivative is once again a quotient law, so I separated it into f and g. We have f is x squared minus 4x minus 16. F prime is 2x minus 4, g is x minus 2 all squared, make sure not to put the squared on the inside, and g prime is 2 times x minus 2. And there is a 1 here, but once again the 1 doesn't matter. So our entire second derivative is x minus 2 squared times 2x minus 4 minus x squared minus 4x minus 16 times 2x minus 2. And you see these crosses out here, I could take out these x minus 2's here. So I took out 2 of this one, so this entire part erases because I took 1 out of the side here and 1 out of the bottom here. This leaves us with 2x squared minus 4x plus 8 minus 2x squared plus 8x plus 32, and these can all just kind of condense and cancel out, and we get the second derivative of our function is 40 over x minus 2 to the 3. Now we need to find our critical values. This one's a lot simpler than the last one. So when f double prime is 0, there is actually no critical value here because 40 will never be 0 no matter what you do to it. F double prime x doesn't exist when 0 is equal to our denominator. You can just find the cube root and makes x minus 2 equal to 0, and we find that our critical value is x equals 2. And now with sign analysis, I'm going to explain to you what this means for our second derivative. The second derivative is necessary for finding something up next called the point of inflection. And the point of inflection is a switch from the second derivative being greater to 0 or second derivative being smaller than 0 or vice versa. And this graphically just is the point on our graph when it goes down, and then it switches from going down from one curve into the next one, and it works the same way going down and up. The point of inflection on this graph can be determined through sign analysis, where you put it from negative infinity to infinity, and you put your critical value right in the center again, and you do the same thing that we've always happened, where you've been finding a value smaller than 2 or greater than 2, and plugging it into your second derivative. In this case, it goes negative then positive. I have these pictures up here to show what this means. So when it's concave down, so the whole graph is kind of like a negative parabola, that means that our second derivative is smaller than 0, so our negative. And this is what it looks like graphically, which I'll explain later when we kind of have to do a little bit of a table combining your derivatives. And then we have concave up, which is just when the second derivative is greater than 0 or it's positive, and it just looks like that. And what this means for our point of inflection is that it's equal to 2 because there is a change, except this just happens to also be our vertical asymptote. And since the point of inflection is the same thing as our vertical asymptote, this point of inflection can't exist at all, and that's why I wrote does not exist. If the vertical asymptote is at a certain point, it can never actually get through that point to do the inflection, therefore it doesn't exist. Now, for our final step of curve sketching, we have to plug everything we just did into this table here. So our table, it's separated into the intervals, and we determine how many boxes there are depending on our sign analysis. So in our sign analysis, we had one where there was 4 empty spaces on either side of our critical values. So we put 4 boxes, and we put the symbols that we put on our sign analysis into the box. So our first derivative, we had positive, negative, negative, positive, and I'll explain the small letters later. And for our second derivative, we only had minus and plus, but we knew that in both directions they were infinitely those signs. So we still have negative, negative, positive, positive. And we'll explain this part after too, but it just has to do with our point of inflection that we don't actually have, but our concave up and concave down. Now I wanted to show you that you have to set these kind of intervals here. So we had negative infinity and positive infinity on the ends of all of our sign analysis spectrums. But it's also important to determine where our critical values are lined up with each other with the first derivative and second derivative. Both of them had a critical value of 2, so it was important that 2 was shown on here. So we made sure that 2 was lined up on both sign analysis that we had. So it was the only critical value for a second derivative, and it was just minus positive. So that's how we knew to put the negative and the positive right here and not over here or over here, because they had nothing to do with the critical values from our first derivative. But we still need to include those because those are important to our first derivative. Now for the bottom, this is where we're actually finding the shape of our graph. And in order to do this, we need to look at the concave up and concave down once again, which we did earlier. So in our first graph here, we know that f prime is increasing in the first box, and that f double prime is concave down. So we look at our concave down picture, and we take our sign here and we look at it. So we know that concave down is increasing on this side because of the plus sign, and just graphically we can see that it's going up and increasing in value. So we take this entire section here and we just plug it right into our table, and we do that for the rest of them. So for f prime, we have it decreasing in the second box, and it's also still concave down. So now we're looking at the other side of it, and we can take this section here and plug it right into the table. Now we have concave up for our second derivative, so now we're looking at this section instead, and it's decreasing, so we look at our first side here, which is negative, it's going down, and we take this picture here, put it back in our table, and we do the same thing once again for the very last one, another concave up, except it's positive instead, so we take the other side and we put that one here.